Welcome to the ICRA 2021 workshop presentation, Learning Robotic Needle Steering from Inverse Finite Element Simulations. Here's a short outline of the presentation. In this work, we addressed needle-based therapies, in which precise needle placement remains a challenge. Robotic assistance has been proposed to both enhance the surgical gesture and to compensate the complex couple between needle and tissue during the needle insertion. In this work, we'll target specifically how the robot can account for the motion of these deformable bodies. The use of naive, rigid strategies for needle steering can lead to huge positioning errors. In green, we can see where the rigid strategies assume the needle tip to be and the result of a finite element simulation of the insertion. The state-of-the-art discusses many approaches on how to model the needle steering and integrate it into robotic control. Both the kinematic models and mechanical energy models assume the needle insertion to happen into stationary tissues and only account for the needle deformation inside them. Finite element models, however, are able to simulate both of the deformable bodies and their interactions. We'll be taking a closer look at the Baksic et al. Approach. The so-called inverse finite element simulations, or IFEM, are a promising solution. As you can see in the video, it is able to perform the needle steering in a complex trajectory while accounting for the soft tissue's deformations. IFEM interprets the needle steering as an optimization problem. It computes an end effector position which minimizes three objectives in the simulation: the tip-to-target error along the trajectory, the entry point motion, and the tangential efforts felt at the entry point. This solution is currently limited by the simulation complexity and can run at 20 Hz to perform robotic control. In this work, we propose to use a machine learning model to solve the inverse problem and command the robotic end effector in a higher rate. The method will learn from iframe demonstrations along 105 straight trajectories. Here are the main variables involved in the training process. We also chose to add uniform noise to the needle target position so it can better generalize to non-straight trajectories. We also compute the tip-to-target error for each time step and the displacement command produced by IFEM. The chosen neural network is called an extreme learning machine, or ELM, with a single hidden layer which presents fast learning speed and low inference time. As inputs, it takes the robotic position and the tip-to-target error and outputs a displacement for the robot to steer the needle along the trajectory. The needle orientation is set to respect a remote center of motion at the level of the entry point. In order to validate our method, we'll test ELM on previously unseen trajectories of both straight geometry and curved geometry. We will also test ELM on tissues with different elasticity parameters than the ones used for the training phase. Results showed the ELM was able to successfully perform needle insertion in all the previously unseen trajectories. When varying tissue elasticity parameters, a small subset of the insertions resulted in unstable insertions and the robotic command drifts away from the target. This occurred for trajectories in the border of the phantom, where the training data is more scarce. A precision analysis shows the ELM was able to provide clinically acceptable precision along the successful trajectories. For curved trajectories, the tip-to-target precision of the ELM remained small, while the IFEM kept a higher distance in average. Further tests are needed to address if this is an actual advantage of the ELM or if it's related to the additional entry point RCM objectives of IFEM. Timing comparison shows a 60% reduction in computational time needed to infer robotic commands using the machine learning approach. As a conclusion, the ELM shows a promising ability to learn from IFEM demonstrations and show relative robustness to trajectory geometry and elasticity parameters variability. Further tests are needed to compare it to IFEM, as mentioned before, and future works will address the entry point variability and more complex simulation scenarios where the computational time advantage might really excel. Here are the references, and thank you very much for your attention.